Good morning, everyone. Today we will be continuing with what Dr. Dhara was teaching yesterday. So, basically, the plan of today's lecture would be after what Dr. Dhara has discussed in regards to Michelson interferometer, which is an example of interference by division of wavefront. Today we will be discussing about interference by division of amplitude and take some examples. But before I do that, let us quickly just for a minute mention one point which Dr. Dhara was mentioning, and I will continue with that. So, what in Michelson's interferometer, basically, as you have seen yesterday, you have a light beam coming from a source, and then you have a beam splitter here. I am not going into the details of the beam splitter because that was already discussed. But what the point I would like to mention is, you can, one of the rays, as we know, it goes up to a mirror here. There is a mirror here. There is another ray which comes. One ray gets reflected by there is a beam splitter here. Okay, that's a beam splitter here. I'm not going all the details, but just so you have a beam splitter here, as he mentioned yesterday. And then one of the rays goes to one of the mirrors, which he called as M2. There was another ray which was coming towards another mirror, which was M1. And then both these rays gets transmitted through, and then we have interference. You can put a lens system here, and you have interference patterns. Now, depending on there are two situations, as if the two mirrors are parallel, okay, then roughly, so this mirror I can think like it's here, the virtual image, because once you see from here, the observer cannot track this band, ray path, but you will feel that the light is coming from a different point up here. So the mirror image of this mirror will be somewhere here, and the point is, if these two mirrors are exactly 90 degrees to each other, these two mirrors will also be parallel, and the source, that the virtual sources you will get from this mirror you say is to the first mirror, and the M1 prime is like an M1 prime because this is a real mirror, but that's the kind of where the M1 prime would effectively be to an observer. Okay, so it's like it will produce two virtual sources, S1 and S2 prime. S2 I call this is a source of S due to mirror M2, and S1 prime is a image of source S due to the reflection everything from mirror M1 prime. Okay, if these two are parallel, then we know we are looking into a longitudinal section, as Professor Dhara was mentioning yesterday, and you would have circular fringes. Okay, an observer here. Of course, with a lens system, there has to be a lens here, what he discussed, which will bring the parallel rays together, and they would interfere to give you circular fringes. Whereas, if there is a slight, these two are not exactly perpendicular, these two mirrors, and you have this beam splitter. Okay. So, you have a beam splitter here, which splits this beam again, but this now they are not exactly. So, this beam may be tilted like this mirror slightly, that is like M1, or in my earlier notation that's M2, okay, and this mirror can be tilted slightly this way, so that's your M1, and again this would pass through the beam splitter, both of these rays, and would come to form to an observer here. Again, the observer cannot trace back this full path of the rays, but instead it will seem like this ray is coming from some mirror which is virtually located here. Okay, that we call as M1 prime. So basically these two mirrors are not exactly perpendicular, but there is a tilt, and so this the source, if this is S source, this from the mirror M2 would seem to be coming from like say S2 prime, and similarly the mirror M1 prime would produce the source S1 prime. Now you can see that the case where you had where you earlier seeing a longitudinal section earlier when the mirrors were exactly perpendicular. In this particular case, they are staggered, okay? And here one would, these two would actually produce, so these are fringes at infinity, located at infinity, which you have to bring by a lens system, but these would be localized fringes, and one would get, a fringe pattern which is like this. So this is a transverse section. So this we had already discussed. I thought I would add to that. Just because of, just point out that if the two mirrors may not be exactly perpendicular. Now this is of course the details he has discussed. I would not go into that. I don't need not. But one point which he also mentioned very nicely is that these two rays are perpendicular to each other and can be used for various experiments. Now over the years, this Michelson's interferometer setup has been used for detection of very fundamental physics over the years. Like if back in 1887 we had the Michelson-Morley experiment, trying to detect ether in theory of special theory of relativity. So so this simple setup has been extremely contributing to fundamental science. Also back even very recently, 2016, the same setup was kind of used in the LIGO, the Laser Interferometer Gravitational Wave Observatory, where these two paths are kind of kilometers long, each of them. And a gravitational wave, when it would come, would actually change the path difference between these two paths, and that would produce a change in the interference fringes. And one could detect the change here and infer about the source of the disturbance. And LIGO, the Laser Interferometer Gravitational Wave Observatory, has detected gravitational waves successfully in 2016, for which we already know a Nobel Prize was awarded in 2017. Okay? So this is a very simple experimental setup, but is extremely rich. Today we will discuss another example of interference, which is division of amplitude. Okay? So let me continue with that. So today what we want to discuss is division of, so this is an example where you divide, we had seen example of Young's double slit earlier, where you had division of wavefronts. Today we want to discuss division of amplitude, and we will take up few cases. So let me show you one picture first. So let me just show you the picture for this thin film interference. So this is the first example we want to discuss. So we will break up this into three examples. One would be a thin film interference, okay, a thin film interference. Then we would discuss the case for wedge, and then we want to discuss Newton's ring. And each of these three cases, all of them goes by division of amplitude. So let me start with thin film interference. So in thin film interference, you can see this is an example which you, on a rainy day, this is very common to observe. When you find that on this wet street, if some oil drop has fallen, like I am discussing this particular picture on the left here, if an oil drop has fallen, you would find that it produces very bright colors when it gets reflected. Now this is an example where you have a very thin oil film on a water, right? Water is beneath there. Or so what is the origin of such bright colors, and why you get such a kind of circular patterns that you see here, right? You get very nice circular fringes here. We call it fringes. We will see that this has to do with interference. Similarly, on a soap bubble, right? This must have blown on this toys you have. You dip it in soap water solution, and then you actually blow on it, and you get such nice bubbles, and they are very colorful. So what causes the color? The soap film is a very thin layer, right? That's what causes such beautiful colors. So we would want to understand those today. Okay, so let us take this example where we would take the first example, say that oil on a water surface. So So what is thin film here? The thin film is the oil films. Okay. So if you want to think like we have rotated the setup here by 90 degrees, and okay, we think that this is a layer which is made up of oil. Okay, and so that oil, so this full layer, so it's like extending out of the board also, right? This full area or this full volume is filled with some material which has a refractive index NF. And when I say that, I have oil in my mind. Okay, and you can have water on this side. Okay, which is so basically we have tilted this picture which we are saying oil on a water side. So we have tilted it by 90 degrees, and then we are looking to the section. So first you have air, then you have oil, then you have water. Okay, that's so here. So I suppose the medium is N1. This may be air. You can think like that. This can be the oil layer. Okay, and that can be your water. Say. So you can have a. So these are each of this indicates the refractive index of the medium. So this is so this medium within this have refractive index NF. So okay, fine. So what we know is that we are seeing bright colors. So light comes in, okay, at some particular angle, and then it gets refracted, and again goes like that. Okay. So of course this is a path. So what we would like to understand is, so and again some parts, not only it will get refracted here, part of it will also get reflected out. Okay, so these are not exactly parallel I have drawn, but they are parallel. So so you have parallel beam of rays coming out. Okay, and what we would like to understand, and so you basically have, of course, this can continue, but let us focus first on these two rays and try to understand. Suppose somewhere you put a lens system, and then these two rays would superpose at some point. So there will be interference between these two rays. Now, if there is interference between these two rays, we know that if we want to find the resultant intensity, we need to find out the phase difference between these two rays. So phase difference here can come from two sources. One would be path difference can lead to phase difference. Also you can have external reflections. So we will bring up each one by one. So let's first discuss about the path difference part. Okay. So what is the path difference between these two rays? So it's very easy. Let us just label it out. So let's call it A, this particular point. Let's call it B. Let's call this point as C. Okay, and I can drop a perpendicular from C to on this ray. Okay, this is a perpendicular. I will call this as point D. And okay, similarly I can break it up into drop a perpendicular from B on the line AC, and this would divide it into two halves. So let me call that as O. Okay, this particular point where it intersects, say O. Okay. And so this picture is available to you through those lecture slides. So even if you cannot see it very clearly here, you can always refer back to the slides and get these pictures. Okay, so this particular angle we will call as theta I, right? The incidence theta I. So of course this is theta T, and similarly this would be theta T. So let me call this as theta T. Okay, and so it tells you if this is theta I, this is also theta I, and so this angle would be 90 minus theta I. I have 90 degrees here, so this would be theta I. Okay, so that is also theta I. And so fine. So what we are interested in is optical path difference between these two rays. Okay, before I go to optical path difference, we can also understand, quickly refer to one small discussion here on your slides. So basically, as we said, we want to understand the path difference, which I already drew here. Okay, so let me just quickly come back to this slide here and point out that if a ray travels a path, say D, okay, in a medium of refractive index n, okay, then the phase gain by this travel, as we know, is 2 pi by lambda times d. Okay, where this is a k times d, and the phase gained we can also write is equivalently. Here lambda is the wavelength of light in the medium with refractive index n. Okay, so I can just write it as 2 pi by lambda naught, and again lambda naught by lambda, where lambda naught is the wavelength of the light in vacuum. Okay, and we know that lambda naught by lambda is nothing but your refractive index n. Then you will see that you can call this as effectively the path that nd. So basically 2 pi by lambda naught, this is the k in this vacuum here, if I multiply it with this quantity n times d, where d is the distance travelled times the refractive index of the medium in which it is travelling, this is the optical path. So, optical path nd, if I is equivalent to the path that this ray would travel in vacuum, and which if you multiply with 2 pi by lambda naught, you get the phase difference. So, wherever in the future discussions I will just multiply a particular distance that the ray travels in a medium with the refractive index, okay, and whenever I want to do the phase difference, I will multiply 2 pi by lambda with that optical path. So, with that, let me come back to the previous discussion. So, what we are interested in here is to find the optical path difference So, optical path difference, of course, so this particular ray AB plus BC is being travelled in a medium with refractive index NF. So, I multiply that with NF, and then the particular distance AD. So, you can see this ray, okay, this particular ray travels an additional distance AD in medium refract N1, the rest everything is same for both the rays. So, this ray has travels an additional distance AB plus BC, and this particular ray, if I call ray 1 has travelled an additional distance AD, and ray 2 has travelled an additional distance AB plus BC. Okay. So, then this would be N1 times AD. That is what we are interested in finding. Of course, then the rest is geometry, we can just quickly do that. So, AB and BC, they are both equal. Okay, and that is, so basically you can find out that would be just cosine theta t. So, cosine of theta t would be your, so let us define this distance, the distance or the thickness of the thin film is say d, small d here. Okay, let us call that a small d, and then this would be d by AB. So, AB is d by cos theta t. So, this is d by cos of theta t. Again, we are interested in AD also. So, let us talk about AD now. AD is this distance. So, okay, so this would be sine of theta I, that is we can say sine of theta I is AD by AC, right? AD by AC. So, AD is nothing but AC times sine theta I. So, AD is AC times sine of theta I. Again, AC is twice of AO by this geometry. AC is twice of AO. And what is AO? AO I can find as tan theta t. Okay, so it is like twice of AO times sine theta I, and AO is like related by tan of theta t, right? Tan theta t is AO by D. Okay. So, AO is D times tan theta t. So, I can write this as, so AO is D times tan theta t. So, this is twice D times tan theta t multiplied with sine theta I. That is our AD which we are interested to find there. Okay. So, again we can use Snell's law here, because we want to relate sine theta t and we want to write everything in terms of theta t say, then that we can get easily from Snell's law. Snell's law tells us, right, Snell's law would tell us that n1 times sine theta I would be nf times sine theta t, right. So, sine theta I have to write, so this would be just nf by n1 times sine theta t. So, I will just write this as 2d, this is sine, this is again tan theta t, and here sine theta I will just write as nf by n1 times your sine of theta t. Okay, so coming back to this, so this is we know. So AB is BC is d by cos theta t, so I have to just do here. So this would then become NF times 2d by cos theta t minus N1, and this N1, because AD is this quantity, N1 and N1 would cancel, so I would just have again 2d NF, and I can write sin theta t as sine by cos, so this would be sine square by cos, so I would have sine square theta t by cos theta t. Okay, so that's what we have, and then we can simplify it, and basically we can take 2d NF by cos theta t common. This would be 1 minus sine square theta t, which is nothing but cos square theta t. So let me just write that. So this cos square theta t and cos theta t would cancel, and the net optical path difference would come to be 2d NF cos theta t. Okay, so that is a path difference that one gets. Another question is, as I said, so this phase difference between these two rays has partly from the path difference and partly from some external reflections it can have. Now that external reflection condition will be decided by the relative refractive indices of these three mediums. So say we can have a situation, let us define, so usually the situation where we have, like as an example, when I was seeing an oil film on a wet water surface, so N1 is typically air, okay, so NF is the refractive index of oil in that example, this is greater than N1. So if that is the case, okay, and you also have, so when NF is greater than N1, this is, and also say NF is greater than N2, because oil is usually much denser than water. If that example you have in your mind, then these two are the usual conditions which will be satisfied. Then you can see this guy, this particular ray 1, okay, gets coming from a rarer to a denser medium. So when it gets reflected here, it will have a pi phase difference because of external reflection, an additional pi phase it will pick up at this in this reflection. Similarly, but the ray 2 goes from when it gets reflected here, it's from a denser to a rarer medium. Okay, so there is no additional pi phase difference for that particular reflection. So whether ray 1 will pick up an additional path difference, phase difference of pi because of this external reflection, ray 2 would not have any such additional phase difference. So the net phase difference would be, you have to, whatever this path difference causes a phase difference, plus you have to consider this additional phase difference. So if this is the case, then the total phase difference between these two rays would be 2 pi by lambda. In this particular case, it's lambda naught, okay, the vacuum lambda, because I am already using the optical path here, times 2d NF cosine theta t, and so this is a part which is caused by the path difference between the two rays, and then there will be a part which is because of this external reflection. So this is a net thing which you have to consider, and when this whole thing becomes this, suppose you call it as delta, this whole thing you call as delta, and then what would be important is to understand whether that delta, so maxima, that means what would be the condition to have a maximum interference. So when these two beams interfere, whether they will do constructively interfere, this would be the condition for maxima. So delta has to be some 2m pi, where m is an integer, any integer. M is any integer, okay. That is the condition when you will have maxima. So you can just put that condition there, and the minima would be, so when they would interfere destructively, that would be the case when delta is some odd multiple of pi. Again, m is an integer here, any integer. It can be, so I am just writing m, but it can be n also, anything. So any integer. So that is the condition. So you have to just fit in, and of course one can solve and get the condition for this. So that is how we can understand. Of course you can see a different situation can arise. Suppose you say when this particular external reflection phase difference you need not consider, you can understand. So suppose I slightly modify this condition and I say NF is also smaller than N2, say a particular case where this medium is denser than the thin film medium. So this is our thin film medium which we are interested in, NF, and when this happens, NF is less than N2, then you see both the rays are going from a rarer to a denser medium in this particular situation, and for that case delta would not carry this additional pi phase difference. So this thing would drop off, okay, if this is the condition. So accordingly one has to modify this condition depending on what the situation is. So what is the what are the relative refractive indices of these mediums? Okay, so this is usually the of course one can also see. So what would be the the locus of these fringes? So what you can see that this has constant theta t, right? So all beams which have comes with the same theta I, because constant theta t would be all beams with the same coming with the same theta I will satisfy this condition. If one of them satisfies, all of them would satisfy. So you would have circular fringes here, right? One can easily see that. This you can also understand from because these two virtual sources would again be, we would be seeing them in the longitudinal section. So you can come back to this. You can, of course I have discussed this, you can go and later you can look into the slides, but I just want to show you the picture. So basically this is the picture where you can see that if you have this particular mirror here and it comes on this, so here the dielectric film is a thin film, and all rays which comes with the same theta I will satisfy this condition, and you will have circular fringes for this particular example. Now just a small comment which one would like to understand is, why is this thin film interference and not a thick film interference? Okay, what would happen if this is a thick film? Will one see an interference? I am already at this, so let me just make a quick comment and then would go further. So of course you can understand that maybe it's not going to be discussed in details in this course, but I will just make this comment here, and you can later look at it. So there are very beautiful books which talks about coherence, and I would refer you to those books in this, like for example by optics by Hecht is a good reference. Okay, so what would happen if you have a thick film interference? So whether we'll have a thick film interference or not, why we always talk about thin film interference, that must be a question which you may have asked or you may not have pondered upon. But the point is that any source which is emitting, of course, has a coherence. The transitions, electronic transitions which gives rise to light, they have a finite time, right? They have a finite lifetime. I mean, so there will be like 10 minus 8 or 10 minus 9 seconds. You can have such transitions which gives you the light, and so these wave trains which comes out are not infinite, but they are finite. Once you have them finite in space, okay, you will always find that they will also have a once they are confined in space, they will also have a confinement in your frequency space, because they are related. Monochromatic light is spread over infinity, but when you combine a lot of Fourier components, we know that you can get confinement in real space. And here is a case where we see that the wave trains which gets emitted from the source are limited in space, because the transitions itself occurs over a finite time. So they are limited in space, which results they also have a spread in the frequency space. So you cannot have a perfectly monochromatic light in these cases, and you will have a finite frequency spread for each of the sources. So it's not going to be so when I talking about lambda here, everywhere we have assumed it's lambda naught, but in reality there will be a small spread over that. Okay, so you will have a delta nu, say. It's not exactly a one frequency emission, but there is a small spread on that. And once you have delta nu, there is also going to be a delta t. That means the corresponding to inverse of this. So this is going to be roughly of the order of inverse of delta nu. So basically this is a time over which you can think like, you know, this wave train, particular wave train is emitted over this time, right? There's a lifetime we're talking about. So that delta t would be related inversely to this. And this is a time one can think like this is a time over which I can nearly think the source to be monochromatic. So this is the coherence time this is typically the coherence time. The coherence time of a source is typically the time over which you can nearly think the source to be, you know, monochromatic, and you know that coherence time, the distance traveled by light in this delta t would typically be their coherence length. Okay, coherence length of a source would typically be, you know, of the order of c. Suppose c is the velocity of light in in vacuum. In a medium, it would be some v. It's typically that's the velocity of light times the coherence time is typically the coherence length. So this is the length, again the finite wave trains, as I said, they're coming, and this is coherence length. So each source is not, you know, coherent over a huge time. So they have finite times over which, you know, the wave trains are getting emitted over this coherence length. So coherence length is a particular property of a source. The coherence length you can think like it's a length over which, you know, the source is nearly, you can nearly assume it to be monochromatic, and you can predict the phase with certainty, okay, at a given point in space. So if this particular thickness, the d, okay, if the d is smaller than this coherence length, then we can have interference, because these two rays which are coming out, okay, the path difference is not larger than the coherence length, because if it's larger than the coherence length, these two rays will have no phase correlation between them, and they are the cross term, right? We were having I is I1 plus I2. So we had discussed this, right? So these are two independent, if the rays individually have intensities I1 and I2, the resultant intensity is some I, which is related to this expression, and delta is the phase difference between these two rays. Now if d is much larger, if the path difference between these two rays is much larger than the coherence length, then this delta would average to 0, okay, and you would not see the effect of this cross term. This cross term would just vanish, and you would just have resultant intensity superposition. There will be no interference. So if to have any observable interference effects, this d has to be comparable or smaller than the coherence length. So that's why you always talk about, you know, typically a helium neon laser, right, 633 nanometers of that order, which has like 0.1 nanometer, you know, spread in frequency or wavelength here, will typically have, you know, a coherence length few millimeters, or it can vary to microns also depending on the sources. So the coherence length varies over a huge range for different sources, and for whatever source you are using, you have to, the d has to be comparable, smaller than that coherence length. Okay, so that's a small digression I took. It is a topic in itself. It is a big topic, and one should look into it more details. And I would refer to you very nice books which are there. But anyway, this is not in this course. We will not discuss about this. A small digression, which I thought, because you know this thin film, why it's thin and why not thick, one may think about it. So it's important to understand that. Okay, then let us go to the next example. As I said, next is the wedge. The wedge case is much simpler, so I will let us look into the picture there. It is a Figure fringes, it's called. Okay, this is again an example which is very common. You may have, in a biology lab or whatever lab, you may have seen that you have two glass plates. You can take, and they are separated by a small spacer. Say at one end of these two glass plates, you put a small spacer, and that would create a wedge like this. Okay, you have a spacer here between these two glass plates, and again in the spacer you can fill up a liquid, right? This whole setup you can dip into an oil, say. So this whole the spacer would be then filled up with some medium which has a refractive index NF, and these two glass plates has say particular refractive index, and then one can see beautiful fringes from this. So this particular thing is known as a wedge, and there is a characteristic angle. So, the angle by which this spacer spreads this two is angle alpha. This is known as the wedge angle. Okay, and so we can define something, and we when we look through it, you see such nice fringes. You see here the picture is shown here. Of course, it has a dependence on the wedge angle, as you can see. When the wedge angle becomes larger, the fringe separations become smaller. So, we would like to understand this process today and see why this happens. This is again an example of interference by division of amplitude. So, let us quickly look into it. So, as I said, this is a wedge that we have here, two glass, it can be two glass plates or any plate. In this particular example, this is glass plates, and this is separated by this spacer, and you have formed this wedge, and say light comes from top, okay, and it gets reflected at this point, okay, and it goes up. This is ray 1, and the other ray gets reflected from gets transmitted through it, and it hits the next wedge and it gets reflected from there. So, that is your ray 2. And what we want to understand is, again, these two rays, so the ray comes from the top, gets reflected at this surface, it goes up, that is ray 1, and another gets reflected, goes transmitted through this wedge medium and gets reflected from the bottom, this top surface of the next glass plate, and that is the ray 2, and then you have a superposition of ray 1 and 2 somewhere here. Now, the question we want to ask is, how would they interfere? What would decide the interference fringes? It is very easy to see that this ray 2 is actually traveling an additional distance here. It goes down the wedge and comes up the wedge. So, if the wedge thickness at this point say is d, then the additional path it travels, it is twice times NF d. So, twice d is the distance, and then you multiply it with the refractive index, as I said, that is the optical path. So, that is twice times NFD. So, that is the additional optical path ray 2 travels, and so again the phase difference due to this additional path traveled is as we said, is twice NFD times 2 pi by lambda naught. And then there is, you can see this, we have kept an additional pi here. You can understand by now this must be coming from some external reflection. So, that you can clearly see ray 1 when it goes through gets reflected at this point, right. This is like coming from glass to say this medium is say air, there is nothing there. And it would be this can be an example where it goes from comes from a denser towards a rarer medium and gets reflected here. So, there would be no additional external phase difference here. Whereas, ray 2 gets reflected from comes from air and gets reflected into glass. So, then from glass, so that is an additional pi phase difference. So, between these two rays there is an additional pi phase which you have to consider, and it is plus or minus, it does not matter, but here we have kept just minus because the condition will not change. This would be the total phase difference which one should consider. And of course, then the question is what is the condition for maxima and minima? Can you kindly take my video up? Yeah, thank you. So, what would be the condition for maxima and minima? So, the maxima, as you can see, would be twice dm. You may have seen that NF we have taken it down here. Okay. So, I have written it this way, so you can actually do it. So, if you are thinking about lambda naught only, so this would be twice NF dm. There is an m additional here because this distance is a function of where you are looking at. So, this x, this d itself is a function of x. So, how far? X of course seems to be the whole distance, but in actuality, so you can define x to be like the distance from this point to suppose this point you call it y, then this d would be a function of y. Okay. So, let us call that this particular distance dm. So, the thickness or of the wedge medium at that point. So, this twice dm. If you are considering lambda naught, then we divide it, you have to think about the optical path. So, that is twice d nf dm is again maxima would be the case because here we have already taken this pi on the other side. Okay. So, the condition usually you see for minima now appears for maxima because of this additional pi phase difference. And similarly, the condition for minima is now the opposite, which you usually see for maxima when you do not have this additional phase difference from external reflection. So lambda is, as we have again mentioned here, lambda is the wavelength in medium of refractive index NF, and lambda naught is in vacuum. So this is the same condition which we have been seeing from a long time. So last 2 lectures, so you would now know that this how to deal with this. So if you have an additional phase difference of pi from external reflections, the condition which you usually see for maxima now becomes the condition for minima, because, and similarly vice versa. Okay, so we can continue with this. We can say that m plus half lambda naught is the condition for maximum is twice NF dm. Now if the wedge angle is small, we can write d as, there is a small problem here in this slide. This x should be till this distance. Okay, so x is not from the point the wedge starts to the point where you are actually measuring d. Okay, so that is d, not the whole distance here. Please correct for that. We're sorry for this, but we'll change it in the lecture slides. So d would be x times alpha, where x is the distance till this point here, and so that would be like m plus half twice alpha, and you can just write dm as some xm times alpha, where xm is the distance from the start of this point to the point here. So that's the distance xm. So this we can write as xm as m plus half by 2 lambda nf, and from here one can easily find the fringe separation. We have started off saying that when you make the wedge angle larger, we see it affects the fringe separation, and of course the wedge angle when you make larger, you are actually changing the alpha. Okay, so then we see this xm depends on alpha, and xm is the distance of the emmet fringe from the point of start of this wedge. And similarly here you can see that the fringe separation delta x would be just, because m is an integer here, delta x would be just lambda f by twice of alpha. It's inversely proportional to alpha. So if you make the wedge angle larger, your fringes would collapse starts, because the separation would decrease. That is again, this can be used for a variety of experiments, trying to detect thickness of, suppose you put a medium here, right? This is a spacer medium. You can put your hair there, right? You can take a hair, which I have very less now, but whatever. You can take a hair there and put between the 2 wedges, and so I don't want to do that experiment. Okay, and then you can actually, that would create a small wedge angle. Okay, the hair, and as you saw that, you can, using this fringe separation, then you look into a microscope, get the fringe separation, lambda f. So you can find the alpha from there, and once you have alpha, okay, the wedge angle, and the distance where you have kept your hair from the wedge starting, and then you can determine d. D is x times alpha. So this can be used to determine the thickness of a spacer material using this very simple setup. But very simple setups can give you very rich physics, which we saw in the case of Michelson's interferometer. So nothing is simple actually. So Newton's ring. Okay, so Newton's ring is the next example which we want to discuss. So we have already discussed wedge, and the third would be your, again this is an experiment you do in your lab. So let's quickly look into the setup that you have often looked at, possibly already by now. So this is a setup where you have a source, and then you have some lens optics which makes it the lens and some optics again here, and you then see that there is the basic setup is, then you have a glass plate, and on top of which you have a lens which has a very large radius of curvature. Okay, and what happens then is, when the rays come down, it gets reflected from here, and then one ray would get reflected from the bottom of the, that's a large convex glass, another ray would get reflected from the glass surface of the top glass plate, and then you will have 2 rays coming towards you, which you can use some optics again to see fringe patterns. So if you blow up this part, this if you blow up this part, this lens and this glass part slide, it may look like this. And then what we want to understand is, what is the, so basically your setup is, so you have a, very large lens, radius of curvature is extremely large, and then you have a, glass plate, and this is a thing, and then light comes down, So part of it will be getting reflected here, and part of it will go through and get reflected from here. Okay, so you may call this ray 1, you may call this ray 2, and then the question again is what is the path difference between these two rays? Now you may have wondered that we don't consider interference between, you don't consider a ray from here and try to see what is the path difference between this and this ray. That we don't do, because again by now it must be clear to you, because this path difference is much larger compared to your typical coherence length of sources. So they would not interfere, there would be just a superposition of resultant intensities. Okay, so such path differences won't matter for your discussion on interference. Similarly, you don't discuss about a ray which goes through and comes from here, because again this path difference would be much larger. Typically this distance is very small. In this scale it looks like very large, but when you have a very large radius of curvature lens on a glass plate, this is a very small distance, and of course this goes towards 0 here. Okay, so this distance is comparable to typical coherence length of sources. So that is the path difference, or these are the two rays which would have any interference effect and which you can actually see. So one would like to understand then what is the path difference between ray 1 and 2, and then for this one can just do some, so equivalent point on this side, if I take, so this is a point and you call this, say that this r is a radius. So here again this is the radius of that point, because you can see this is a lens, so this point would be occurring on a circle. So this is the radius of that circle, say this is where this distance happens. Okay, and this is a radius of curvature of the lens, say from this point to this point. So r is the radius of curvature of the big lens, and small r is the radius of the ring. So then we can find this distance. What we are interested in is this small d, because this same small d is happening here. Okay, then that d is nothing but r minus r square minus r square. That is what the small d would be, and one can just work that out. I will come back to the slides again. One can just work that out. So this would be r minus r square minus, as I said, and typically r is very large because that is the radius of curvature of your lens. You can do an approximation here and drop the higher order terms and just retain the first leading term here from 1, and then you just have r square by 2r. So that is the typical path difference okay, between these two rays, as we just saw, because this additional twice of this is the path difference, because this ray 2 travels this distance twice, okay, more than the ray 1. So then that's 2dn is the, again n is the refractive index of the medium within that say where the lens and the glass plate, you can dip it in oil, say, and then the spacer medium would be filled with oil, which can be of refractive index n, and then we have to say this condition is 2dn, that is the path difference. If you do not considering phase change of pi for one of the rays, this is the case given here, and this is for bright rings, right? This is a condition which you usually see for dark rings, but here it occurs for bright rings, because you understand that while the ray which gets reflected from this ray 1, if you talk about ray 1 gets from a denser to a rarer medium. Suppose this is air, okay, within this wedge part, this is nothing, no medium is there, this is just air here. So then ray 1 goes from a denser to a rarer medium, there is no phase change of pi, no external reflection, whereas ray 2 is going from a rarer to a denser medium, so ray 2 would have an additional phase change of pi. So this additional pi is taken care of here, and the condition which you usually see for bright rings now occurs for dark rings. Okay, that's the means the condition you see for bright rings without considering an external phase change would change now, and one can of course do d, as we said, d is d is r square by 2r, and from there one can find the radius of these bright rings, and you can write it, m is an integer here in this expression, we can just use this, and basically similarly the dark rings condition is now changed, in a sense that you have considered this additional pi phase difference, and this would be an integer multiple of lambda by 2. Again, m is an integer here in this slide here. So of course, this is the physical understanding that when you have a bright fringe, when this pi phase difference is considered, this would look like the conditions. This is just constructively interfering or destructively interfering, which we have discussed, and the same is shown here. Okay, and you can see that this constructive interference condition, you can go through this, you will see that here the two rays, they are one on top of each other, so that's why it's a bright fringe, and here it's not the case. And you see this will be such bright nice rings, because again here this depends on the locus of this constant d, right? The locus of constant d here in this particular setup is a ring, right, and a circle, because this constant thickness, will occur on a constant circle. So wherever you have a constant d, that is the locus, the fringes will also have the same shape. So these will be circular rings here in this setup, and this is a typical example. Another very interesting thing which we observe here is if you I just want to make a small comment here, is that this this area between the two rings, area is conserved, because if you see that this r square, for instance, if I look into here, r square, pi r square is the area typically. The difference between two fringes is a constant quantity, because this will, so the area remains constant between two Newton's rings. So if you make larger and larger, the overall area remains conserved. So if you have larger rings, they becomes narrower and narrower, whereas if you have smaller radius, you have larger area. So that is a typical experiment one can do in the lab, which we will do, and I think you can always put your questions and comments, and we'll discuss that. Thank you, and yeah, I'll finish.